Hello everyone, this is a video lecture for Linear Algebra Chapter 3. So just like the last time, we're going to be going through every single section of Chapter 3 here, briefly. So let's start with 3.1, Determinants. Determinants. There you go. So what are determinants? You might have seen them before, probably not, but maybe. Let's just say, let's start with an easy one. We have 1, 2, 3, 4. And they want the determinant of A. Another way to write that is with these absolute value signs. They're not absolute value signs, they're just vertical lines, but that's another way to write it. So, determinant A, what is that? So, determinant would be, now instead of the square braces, you're going to use vertical lines. It indicates that you're doing a determinant. And so what I'm going to do is 1 times the 4 minus 2 times the 3. So 1 times the 4 minus 2 times the 3. When we get 4 minus 6 is negative 2. Notice that I'm resulting in a scalar. It's a scalar answer. I take a whole matrix and I reduce it down to a single number, basically. What does this number mean in relation to the original here? Not much. Going from here to here is impossible. It doesn't do much. Even saying, well, this gets that, it doesn't tell me much. There are a few things, like if this was a 0, that would say something. But just getting any other kind of number is not particularly useful. So I'm just showing you what that is. What I'm going to be using it with is proofs and some kind of applications, but these numbers going to this numbers does not mean anything unto themselves. You have to have context in order for any of this to make sense. Here's another example. Let's do a 3 by 3. Now, one thing about determinants is that they gotta be square. Notice that 2 by 2, 3 by 3. With 3 by 3s, it gets more complicated, and I'm going to use a different color to show you what's going on here. Basically, we have, I guess, one particular row or column that we're going to choose to be our cofactors. And so I'm going to start with this up here, and I'll show you what I'm going to do here. And then I'm going to expand their minors. So here we go. First off, I say 1 times, and that's going to be a positive 1. I'll fill you in on positive, negative stuff in a minute. It's going to be kind of weird. But positive 1 times, and then I have this determinant here, which I'll just rewrite. 5, 6, 8, 9. Okay. And now I'm going to choose this one. And so then, basically, notice I guess you could say, the form that I'm using, how I'm doing this. 2, 3, 8, 9. Notice that the red crossed through up here, and I left that was my minor. Here I'm crossing through the middle, so I'm leaving the 2, 3, and the 8, 9 behind. And then finally, if I'm choosing this guy, I have a positive 7 now. Why a negative right there? Again, I'll tell you in a minute. And then if I cross through the bottom, I have, like, this is the leftovers, I guess you can say. Okay. So, is long, just for a 3 by 3, pretty long. And so I have to keep going. What I'm going to do is find the determinant of each of these individually. So 5 times the 9. I'm not very good at making dots. I'm just going to use parentheses if that's okay. Minus 6 times the 8. Because we know the determinant of a 2 by 2. It's right there, that same format. So that was a positive. Now a negative 4 times. And then here we got 2 times the 9. And then minus 3 times the 8. And then a plus 7. 2 times the 6. Minus 3 times the 5. Whew. That's good enough. Okay. Doing all this crazy math, what you actually get is a negative 3 plus 24 minus 21 makes a 0. Now, having a 0 determinant actually means something. I'm not going to go into it right now. We'll see more of those later. I did this a little wrong. There was actually, I shouldn't have put an equal sign. I probably should have put like a little arrow thing, because this over here is the determinant of A. It's no longer equal to A. So the determinant of A is equal to all this stuff. Not A itself is equal to this stuff, okay? That was a small little mistake, but, well, we get over it. Okay, cool. So now you've kind of seen the process of it. Let me show you why we got a positive, negative, positive, and all that stuff. There's 3 different things that we're going to need to know about these bigger matrices. We have the signs of the cofactors. And so for my 3 by 3, it's a plus, minus, plus, minus, plus, minus, plus, minus, plus. And a 4 by 4 looks kind of similar, and a 5 by 5 and all that stuff. So those are my signs. Notice that I was using these 3 here. Thus, I would have had a plus, minus, plus. As I was using these as my signs in the front, plus, minus, plus. Okay. My actual cofactors are the numbers that I chose here. Okay. Those are the actual numbers that I chose here. In this particular case, it was the 1, 4, and 7. So those are my cofactors, my numerics, I guess, and you can see the 1, the 4, and the 7. Okay, so I chose those as my cofactors, and then I have my minors like major, minor kind of thing. And because I was choosing this here, what we actually had when I crossed it through was the 5, 6, 8, 9, and then the next one that's an and sign. I crossed through these guys and had a 2, 3, 8, 9. And then another and sign real quick. I crossed through. See, I messed up. No, I did. I'm fine. I crossed through these 2 guys here, and I had a 2, 3, 5, 6. And so those are my minors. Again, they're just smaller little determinants. Okay. 2, 3, 8, 9. And then over here, the 2, 3, 5, 6. Okay, so those are minors. Okay, so now you have some verbiage for whenever I say something like cofactor, minor, something like that. So when they say it or whatever, now you know. Okay, let's go on to one more thing. If my A matrix is triangular, and I will show you what that means here in a second, then the determinant of A is equal, again, to the determinant A like this, is equal to A11 times A22 times A33 times all the way down. It's the product of the diagonals. Product of the diagonals. So what does that look like or mean? Let me just give you an example again. Just kind of doing example time right now. Let's say that I had 1, 2, 3, 0, 4, 5, 0, 0, 6. This is a triangular matrix because I have the upper triangle, and then the lower part here is all zeros. So that's what makes it triangular, is that we have the diagonal is filled in with numbers, but either above or below it are all zeros. Okay, so what I'm saying is the determinant of this guy is super easy. I'm just going to multiply my diagonals together to make 24. Very, very simple to do that. And so what they're trying to show you is tricks, I guess you can say. Tricks on how to get this stuff done quickly if you need to, or if you can at all. So here is another example that we're going to do. And there was very few proof questions, and I didn't want to do one that was on the quiz. So I'm just doing a couple like semi-proof questions. We will have a proof or two today, but not. It won't be as strenuous, I guess you could say, as the other chapter 2 was. So I have these lambdas. Those there are lambdas. Again, it's just kind of like a line with a little extra foot. So lambda, just a Greek letter for L. And we have them all down the diagonal. This is actually all in that one element of the diagonal there. And so I'm saying this determinant equals 0, and we're going to solve for lambda. What does lambda equal to in order for all this stuff to be? And so it's like a solve for x. I know we could just make these an x, and there you go. But that's not the point. Okay, so how am I supposed to find this big determinant here? Well, you pick something that's going to be your cofactors and stuff, and you can choose any row or column to be your cofactors. And so I'm going to actually do these guys right here, just to prove to you that you can do something not just the first column. You can do the first row, you can do wherever you want. It could be any kind of row or column that you like. But I'm using those in particular, again, just to show you as an example you can do this. So let's say I have this guy. I'm going to cross through this and use that as my minor. So lambda times lambda 3, 2, and then this lambda minus 2 again. And now notice this is, again, plus, minus, plus. So that's a plus. And now a minus. I'm going to use 0 times whatever. It's kind of funny because the 0 times whatever is going to be 0. It's not going to actually change anything. You can just get rid of that right now. Plus, and then 1 is in the front. Now we're doing this guy right here. 0, lambda, 2, and 2. Okay, awesome. And this is, of course, still equal to 0. We'll do more on that here in a minute. So lambda's in the front, and here I'm going to actually, multiply across. So I got lambda times lambda minus 2 minus 3 times the 2. 0 didn't matter. This guy right here is pretty easy. 0 times anything is 0. So we can get rid of that too as well. And then lambda times the 2. My lambdas are kind of looking like parentheses a little bit. I'm going to distribute this guy first. And so we got lambda squared minus 2 lambda minus the 6. Over here we can get rid of that. And then we got minus 2 lambda. Distribute this lambda. So we got lambda cubed minus 2 times lambda squared minus 6 times lambda minus 2 lambda. Combine like terms here. Lambda cubed, 2 lambda squared, negative 8 lambda. And this is still equal to 0. So now solve for lambda. This should be pretty easy. I'm going to factor a lambda out. Oops, now it's a square. Okay. So now from here I could say that lambda is equal to 0. There's one of my answers. This here can factor down. And you could use quadratic formula if you really need to on something like this. But honestly, this one's pretty easy. We're talking about 4 and 2 that it should factor down to. So negative 4, positive 2. And so then what we have here is lambda equals 4. And lambda equals negative 2. And there we go. Cool. Let me pause the video for just a second. All right, I'm back. So we have our 3 answers, 0, 4, and negative 2 for lambda. Very easy. Let's go on to the next section. So here we go. 3.2, determinants and elementary operations. So determinants and elementary, I don't think I spelled it right. I'll do LM. Row operations, I think, is kind of what they're wanting to get at. It's elementary operations, but row operations is more what we're really doing here. So I went looking through the section, and I got to say, at first when I was writing it down, I basically just said, well, I don't see anything important here. Let's just move on. And that was that. But I do have questions about this on the quiz, homework, obviously. So I want to make sure that you see just a couple of things. So this will be very fast on these, I guess you could say, elementary row operations, but here we go. If you're doing a row operations, like a row swap, this kind of goes way back to chapter 2, might even be chapter 1 a little bit. But like if you're going to swap out 2 rows, then basically, and I'm saying, we got to understand here, I start with a matrix A, and then it's going to be going to a matrix B, and I'm swapping these 2 rows, call that a swap. Then the determinant of B is equal to a negative determinant of A. This is a pretty important little rule. I know this sounds kind of weird, so I want to show you in physical example with numbers. So 1, 2, 3, 4, and what if I row swap these? Okay, so then I actually now have, this was my A, but now this is my B, a 3, 4, 1, 2. Well, what's my determinant of this guy versus this guy? Well, the determinant of A, if you can see, is 4, again, minus the 6 equals the negative 2. But here, determinant of B, I got 6 minus 4 is a positive 2. You can see that they're opposite sign of one another. Now, this is not a proof here. I'm just basically stating a property. This is the property here, that if you row swap, then you can do, you could just say the determinant's a negative value, okay? Another one is if you do, I guess it would be like a row multiply. So I'm going to do a row multiply, and we do this C times R1 equals R1 or something kind of like that. Basically, I'm multiplying a number into a particular row. Again, remember that A is going into B. It's changing from A to B. So let's say that I have my A, again, 1, 2, 3, 4. And my B, I'm going to multiply, let's just say I'm going to multiply the top here by 7. And so then I got 7 and 14, 3, 4. So what are my determinants now? Let's see what happens here. So the determinant of A, again, we already know is -2. The determinant of B, I got here 7 times 4. I'm going to have to get a calculator out. Minus 14 times the 3. Hold on. I was just picking a number at random. 7 might have been a little bit big. I got -21. Was that right? 7, nope. I am incorrect. Hold on. 7 times 4 minus the 14 times the 3. I had mixed it up a little bit. Sorry. I thought that was looking a little weird. -14. I make mistakes too. It's okay. So -14. Notice the difference between these. What makes these similar / different from one another? Well, basically, it's this guy times that 7 to make the -14, right? This guy times 7 makes that -14. So what's going on is that the determinant of B is C times the determinant of A. If you only multiply it by a single row, it alters the entire determinant, okay? So there's something else that we would have to know there. And the last one, I guess this is like row addition, but it's a little bit more than row addition. We've done this in the last chapter 2 here. I would say C times row 1 plus row 2 equals row 2. I'm multiplying something into from row 1 into row 2, and it's going to now equal row 2. It's kind of a weird thing, but the determinant of B, because we're going from, again, A is going into B now. The determinant of B equals the determinant of A straight up. Now, I definitely want to show you this one. Remember that determinants must be square from square matrices. So I got a 1, 2, 3, 4. And so I'm going to do, let's just say -3 times row 1 plus row 2. And again, the book often just stops right there. I like to go a little further, equals row 2. What I'm trying to do is make this into a 0. This is all back from chapter 2 here. So I got 1, 2, doesn't change. And then here I got a 0 for sure. -3 times the 2 up here is -6 plus the 4. It's going to be a -2. And now I want to find the determinant of these guys. Remember that the determinant here of A is a -2. The determinant here of B, if you can see, is 1 times the -2 minus 2 times the 0. Well, 0 times anything is 0, and we're left with -2. They're equal. They're the same. So whenever you do this sort of row operation, it's going to have the same determinant. Awesome. Well, it's kind of interesting because, like, I could show you here with an example, and in the book they say, aha, well, look, all 3 of these are proven. We're good to go. Well, the homework, I'm sorry, the quiz, and right now I'm going to do a similar problem, is, hey, prove that this property works. So let me write this down in links. So when I don't know what I wrote there. That's kind of weird. I just wrote the same word twice. When obtaining B from A by adding a multiple of a row of A to another row of A. Okay, now come on, pause for a second. All this right here is basically just saying right here. I'm just stating this thing right here. Row addition with a little multiplier in the front, okay? Then the determinant of my B is equal to the determinant of A. Awesome. So I'm proving this last thing right here. I'm proving this. Now you might think, and this is incorrect, you might think, oh, well, look, we just proved it. We did that. No, 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 no. What you did was you showed me an example of a 2 by 2. In fact, it's even tougher than what you might think, because if you're going to go, well, we got A, B, C, D, and we're going to now do blah, 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 blah. No, 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 no. They never said a 2 by 2. They never said a 2 by 2. They said any size. And we're, of course, suggesting that these are going to be squares because we can do determinants. Where do I even start? Well, it's funny because on the quiz you're going to be doing the 48, which is very similar. So I'm going to show you my style to this. And I am not going to be able to get you a perfect answer here. I'm just going to do it kind of halfway, okay? Now, I'm not looking for the best answer, especially with, again, on the quiz 48. If you were to see my answers, which eventually I do send out my answers on these things, it won't look very proofy. It'll just kind of be a whole lot of numbers flying all over the place. I'm going to do my best to talk this through with you and have it still coherent, okay? So I'm going to just assume that we have B is from all this stuff. So here we go. I'm just going to assume this thing here. This is not very proofy. I'm not looking for perfection here. Little c times, I guess it would be like R1 from A plus R2 is equal to R2, and this is all A. Now, what this is going from a matrix A into a matrix B. So let me go ahead and show you what my A is. A11, A12, so on and so forth. A22, no, I'm sorry, 21. A22, row, column, etc. I already know I'm going to need a little bit more room here. Let me get rid of this thing right there. Okay. And I'm going to say continue, continue, continue. And then we've got now a H1, a H2. We got a I1, a I2, so on and so forth, all the way down. And this might look messy, but this is legit. This is actually what my answer looks like for this kind of problem. I know that sounds really weird, but hey, I mean, we got this big matrix A set up. Well, let me now write what B would look like. It's very, very similar. 1, 1, 1, 2, and I'm not going to put all the dots every single time if that's okay. Got these guys. Well, what's going on is that I'm going to take C times this row and add it into this row, okay? Again, there's a little bit of words up here saying, taking, C element of the reals into row H plus row I or something like that. You can use IJ, I think. I had a J down here. I don't know why I didn't use it, but whatever. So that's what I'm going to do. C times this thing and add it into this guy. And so what I actually have, if you keep going, is I would still have this row here. It doesn't really change. But this now is become C A H1 plus A I1. And then this guy here is C A H2 plus A I2, and so on and so forth forever and ever. Okay? Notice that it's just this single row that's changing. Nothing else is going on here. That's the only thing. And I want to know what the determinant of B is. I'm trying to prove that it's the same as A, and we'll kind of work backwards to get all to that. Well, I'm going to choose, I'm going to use a different color, I'm going to choose my cofactors to be these guys right here, actually. This row is going to be my cofactors. And I know that looks really weird. Normally we just use the first column or the first row, but you can use anything you want. I'm going to assume that is a positive, negative, but it doesn't really matter in the end. I'm just kind of going with the flow, not doing it too intensely. This is not a very intense proof. It's just kind of a work through it, and I get the idea. It'll be fine kind of proof. CAH1 plus AI1 times, and then here's the big thing. I have this big old matrix here. with my minors. If you recall, because I'm choosing this cofactor, I'm going to have to get rid of all this other stuff and have this whole thing and this whole thing right there. You probably could, summarize it as something like, you could say minor, a like I1, minor I1, I think is fine. But that's what I'm doing. I'm taking all this chunk and all this chunk and throwing it in right there, okay? I think that'll be a little bit more concise for this recording. And then my 2's, AI2, and then times my minor of I2. And then plus, and so forth. Okay, cool. So that should be my determinant if I were to do it that way. Wow, that's pretty big. But again, I'm not wanting to go through every single specific. What I'm going to do is basically distribute these into each one of these. And so I got a C, AH1, MI1, plus AI1, MI1. And then I got a minus sign, C, AH2, MI2, minus again, distribute, AI2, MI2, and then plus, and so forth. What's actually going on here is, again with a different color, this right here and all the way down actually represents, or is, it's equal to the determinant of A. Go back here for just a minute. Let's talk about this. Right here, if I were to take these as my, cofactors and then my minors, I would get my determinant of A immediately. That would be my determinant of A. So that's what I'm saying is all this chunk here is the determinant of A. And we got this kind of mess here that hopefully, because again, I'm supposed to be making this equal to the determinant of A somehow. How am I going to get that? I don't know. Well, the only way is that I have this determinant of A here. This stuff must equal 0. That's going to be the goal. All this stuff here must equal 0. I don't know how yet, but I'm going to keep going. How I'm going to make this work is I'm going to now say C times, put a C in the front because they're all going to have a C, AH1 MI1 minus AH2 MI2 plus ... cool, and then plus the determinant of A. Okay, so I factored the C out. I'm writing it all in one line, and I made that determinant A for sure its own entity. And so now I'm just looking at this chunk here, and this is the only thing. It must equal 0 for this thing to keep going. That's the only way I can make it work. So I'm going to tell you, I went on the internet. I was going to look through a couple ways to make this happen. And I didn't find the exact proof, but I found a hint that really helped me. And so I'm going to show you the hint that was given to me on the internet. Looking this stuff up is not bad. Just don't use it as a crutch. Use it as a tool. So, how do you make this work? Well, you actually take this and you go back into a determinant of a matrix of some sort, okay? So we already used C, A, and B. Basically, B is what we're going to try to find here. So I'm going to use D, if that's okay. I'm going to rewrite this whole thing here as determinant of D, and then here, this is determinant of A still. I'm rewriting all this chunk here as determinant of D. How does that work? Well, just like I had here a scalar times a minor, a scalar times a minor, a cofactor times a minor, basically, made a determinant of A. What if I went that same style this way? I said I have a cofactor times a cofactor times a minor. Cool. Well, if that's the case, what does D look like? What does the matrix D look like? A11, A12, A22, A21, A22, so on and so forth. And if you keep going down, we're going to have the AH1, AH2, and here's where it gets a little weird. This right here was the cofactors for that row beneath the AHs. Okay? These are those cofactors. These are these scalars. This is right here, this same row, that row of i's. The row I, it's not row I anymore. It's row whatever this stuff is. Okay? So wherever I used to be, I'm now using these numbers, well, this number, as my cofactors. And so yet again, I have an HI or H1 and H2 and so on and so forth. And then I would have the J and all that stuff beneath it. Okay, cool. What I'm getting at is I'm kind of like reversing the process. I'm going backwards in a way. I'm saying I have all this big list of minors and cofactors. These are the cofactors for the row I, for my row I. So my row I, where, H, I, J, my row I is now replaced with these cofactors. They just happen to be H's now. Well, here's the interesting point, is that notice that these two rows are the same. So I would say rows H and now I, that's row I technically right there, are identical. Identical, I think I spelled that right. Okay, great. They're identical, and so if you go through this process real quick, basically, if you have two rows that are identical, they're equal to 0. The determinant is equal to 0, and you're done. So you could just say, the determinant of D is equal to 0, and now we're done. That's not good enough. I mean, that's true, and, if you know what you're doing, that's fine. But why is it equal to 0 if we have two rows that are identical? Going way, way back, way, 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 way back, right here, row swap. Out of all the things, row swap is useful today. If I'm swapping these two rows, they should change their sign, okay? But now notice if I had identical rows. What if I had 1, 2, 1, 2 in a way? So like on the side here, 1, 2, 1, 2. And I swap them, right? Well, then I get 1, 2, 1, 2. Okay. What's the determinant of this guy? My determinant of this guy right here is 2 minus 2 is 0. Well, the determinant of this guy is 2 minus 2 is 0. I'm not saying, oh, they're the same. I'm saying, look, if you row swap and you get the exact same matrix, then the determinant was 0 to begin with, because the only way you can have the determinant of these two matrices, two separate matrices, be the same, yet sign is different, is to have them both equal to 0. Basically, 0 equals a negative 0. That's the only way that you can make those numbers match up in this case. Of course, I tried to show you a little example on the side, but I'm assuming this. I'm going to say assuming this row swap thing is a true statement. So right down here, assuming that the row swap of the A and B, A to B, determinant A is equal to a negative determinant B, kind of stuff like that, right? I would say then, because they're identical and assuming this stuff here, then the determinant of this D here must equal 0, as it is the only number that can satisfy this equation here. Blah, 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 and more words. Okay? So therefore, now we have C times determinant of D plus determinant of A, and this is equal to determinant of B this whole time. Well, this is now 0. And you can just get rid of that. There you go. You're done. Solid box thingy. That was a lot more words that I said than what was written down. I would suggest to type a little bit of words about what you're thinking. But in the end, this was a little bit difficult of a proof. It's hard to describe, with all this numbers flying around. It's very difficult whenever you don't have a specific size. So do the best you can. I'm not looking for perfection, but as long as you can get the idea down, talk to me about it, and I use my words. I didn't write everything down just for time's sake. But if you talk to me about it in your proof, then you're telling me what's going on. That's helpful, okay? All right. Next section, 3.3, properties of determinants. So let me just list out a couple that caught my eye. Determinant of A times B is equal to determinant of A times the determinant of B. So you can multiply them on the inside, you can multiply them on the outside kind of thing. The determinant of c times a is the c to the n times the determinant of a. Now that's assuming that a is an n by n matrix. I don't know how you would say it, reals n by n, something kind of like that. I can't remember the notation, but basically it's a matrix n by n. A is invertible if and only if, we're going to talk about that here in a second, the determinant of A is not equal to 0. Now, whoa, slow down, pause. This is my first time I saw this little guy right here. If. That is if and only if. If and only if. I might say this one time on a quiz, like the first time I use it, but as we keep going, I'm going to just say IFF. You might think I've typoed. You might think, oh, well, he meant if instead of just if. You know, I just pressed the F key 2 times. It is not a typo. This is an actual term, if and only if. What this means is an if statement, if then, is singular direction. You start with the if, you get to the then. An if or only if actually goes both ways. Okay? I don't know how to write the other side. I don't know. It's both ways. What you actually have to do is 2 proofs at once. 2 proofs at once. 2 proofs. You're going to go, let's say you're going, do something like this here. A, if or only if B. So then you're going to go from A to B. That's part 1. Part 2 is you're going from B back to A. You have to do both. You have to do both in your proof to actually make it true. Okay, so I just wanted to tell you that ahead of time. Now they're saying that A is invertible, then therefore the determinant of A is not equal to 0. Cool. Or the determinant of A is not equal to 0, therefore it's invertible. You can use it either way, but they already proved it both ways. You have to if I say if or only if, you're going to have to prove both of them, one to the other and the other to the one. Okay? Little side note there. The determinant of A inverse is equal to 1 over the determinant of A. I think that's kind of weird. I mean, yeah, you know, -1 power means to flip it, but somehow it still works. It's pretty neat. It's pretty neat. And then the determinant of A is equal to the determinant of A transpose. Do notice here, though, that we're talking square matrices, so when you transpose, it's not changing its size here. Okay, so there's just a couple that stood out to me. I'm not going to do any in particular, but 3359. Whoops. Kind of zoom out again there. 3359. Here we go. Let A and B be n by n matrices. You can see why I'm saying this stuff instead of writing every single word I can, because my handwriting's so bad. That's okay. Be n by n matrices such that A, B equals I. Prove that the determinant of A is not equal to 0 and that the determinant of B is not equal to 0. Okay, this is just an if statement. If then. So I'm saying that I have this AB equals I, therefore they don't have a determinant equals 0 kind of thing. That's good. What I'm going to start with is, suppose, I'm going to make this more formal, I guess you can say. Suppose that we have AB are n by n matrices such that AB equals I. So I'm just restating the original thing. Assume, suppose, whatever I'm going to use. I use suppose here in this particular case. Because I have that, I'm going to now say, thus, my B, either way is fine, B is equal to A inverse. Okay? B is equal to A inverse. That's the only way that this could happen. because then you have A times A inverse is equal to I. That's a proven statement back from chapter 2 there. I guess you can use a little box if you want to say that. Just talk to me about it. So if A has an inverse, it is invertible, and therefore the determinant of A is not equal to 0. What I'm doing is I'm going back by theorem or property, something like that. I don't know. Let's just label these 1. I'm just making this stuff up. 2, 3, 4, and 5. So according to property 3. So property 3. Notice that I'm trying to reference back to what I had done earlier. What you would use is whatever the book says, or you can say by the property of matrices. Honestly, you don't even have to say this at all. I get the point, but it is good to tell me where you got this stuff, because sometimes we're like proving these properties. It kind of just depends on the problem. But this is a good little thing to have there, okay? So we got determinant A not equal to 0. Cool. Well, I also know that the determinant of B is equal to the determinant of A inverse, which is equal to the determinant 1 over the determinant of A. Again, by property, what was that, 4 or 5? 4. By property 4. Just making that up. It's not really property 4. I have no clue. I'm just saying property 4 because that's what I have written. And so, cool, we have this guy right here now. Well, notice that my determinant A is not equal to 0. Okay, it's any other number besides 0. 1 divided by the determinant of A is not equal to 0. Well, ever. Just, it can't ever equal 0. Even if you had the denominator equal to 0, it still wouldn't equal 0. It would equal infinity or whatever. So, we're undefined. So, this is never equal to 0 for all, I don't know. This is weird. For all determinant of A element of the reals. This is not required. I think it's just silly. I'm just basically saying always. Oops, sorry. Always. I want to say the word always. When is this? It's always. Therefore, the determinant of A is not equal to 0, and the determinant of B is not equal to 0. Done. So there you go. Not too bad. Next and last section, 3.4, applications of determinants. Okay. I want to show you two particular things that they talked about. We got Cramer's rule. So let's talk about Cramer's rule for a second. We have a system of equations that needs to be solved. AX equals B kind of stuff. This is very vague language here, okay? What I'm really wanting to say in example land is something kind of like this, and what I want to do is RREF it. That's what I want to do to solve for X and Y kind of stuff, okay? So we have some kind of system kind of like that. The Cramer's rule is basically my X is equal to dx over d, and y is equal to dy over d, and z is the same thing, blah, 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 blah. However many you want. Well, what is dx and d and all this stuff? Well, d stands for determinant, of course. I'm going to use this as an example of what we're doing with Cramer's rule. So I'll actually use Cramer's rule on this one, just to show you what it's all about, okay? First off, d is the determinant of the original 2x2. Again, this could be a 3x4 or whatever. Again, this is my d. That's my area right there. Pretty simple. So I got 5 minus 8 is equal to a negative 3. That's an important number. We'll be using it a lot. dx is kind of strange. What's going to happen is I'm going to take this, my answers, and replace my x column with that. I'm replacing my x column with my answer column. Okay? Do you see what I have there? Instead of the 1, 4, I now have 3, 6. That's my answers. And then find the determinant. I got 15 minus 12 is equal to a positive 3. Cool. My dy is very similar. I'm going to replace my y column now with the answer column. And so then I got my 1, 4 original x's, and then the 2, 5 No more, not 2, 5. It's 3, 6 now. 6 minus 12 is a negative 6. All I do now is simply say my x is equal to dx over d. So I got 3 over a negative 3 is negative 1. And my y is dy over d. I got negative 6 over a negative 3 equals a positive 2. And those are the answers. If you remember back from Chapter 2, we did RREF of this thing before, and we got those answers very, very simple. Okay. Okay, cool. I know that there's a question on your quiz about the plane equation for some set of numbers, and it's pretty cool. I'm going to do the equation of a line. So it's very, very similar, but I'm using 2 points instead of 3. So basically, I'm doing a smaller version of what you would be doing on your quiz. Okay. The formula for my determinant here is the determinant of this matrix. Here we got x, y, x1, y1, x2, y2, 1, 1, 1. And this is equal to 0. That's my equation. If you're going to be doing a plane, you would just extend this out to have a z and still 1s, and then you have another set for another point there. We have 2 points to make a line. I'm just going to make 2 points. Well, that's not fun right there. There we go. 2 points to make a line. There you go. Cool. In 3D space, you need 3 points to make a plane. And that plane basically extends out like a piece of paper, but it looks like a triangle when you connect the 3 together. Okay. Cool. So now let me just go ahead and make some points up if that's okay. 1, 2, and 3, 5. If I did 4, I think it would turn out kind of dorky, so we're going to do 5 to make it a little bit more interesting. So those are my 2 points, which are going to go here and there. And so here we go, the determinant of, actually you don't have to write the determinant, you just vertical lines here, x and y as variables, 1, 2, 3, 5, and always a 1, 1, 1. This should equal 0. Solve for y, I guess you could say. Okay. So I can use any one of these rows or columns for cofactors and minors and all that stuff. I'm actually going to use these as my cofactors. So this is going to be a positive, a negative, and a positive. If you remember the signs of your cofactors. And so I've got a positive 1 times, and then not these guys. Remember, you're doing this kind of thing for the top one there. 1, 2, 3, 5, minus 1 times. Now I've got my x and y. Do not replace those with something else. It's very important to keep them as x and y. And then finally, x, y, 1, 2. So here I've got 5 minus the 6 is going to be a negative 1. This is where it gets a little weird here. I actually got a 5x minus 3y. And then finally on this side, I have 2x minus y. Well, if you distribute this, I got negative 1 minus 5x plus 3y plus 2x minus y equals 0. Again, this whole still thing equals 0 here. Combine like terms here and there. Negative 1 minus 3x plus 2y equals 0. I'm going to move these guys to the other side. 2y is equal to 3x plus 1. Divide by 2 on both sides. 3 halves x minus, plus 1 half. And there is my equation of the line. Now, when you're going for the equation of a plane, you can do z equals, or you could just leave it kind of like this, I guess is fine. It's either way, really. That was just an example. We still haven't done the real problem for this section. So I'm going to try to do proofy ones. This is close to the one that we were going to do in the quiz, but not quite. So here we go. Prove that if the determinant of A equals 1, that looks really sloppy. The determinant of A equals 1, and all entries, they say entries, I say elements, in A are integers. Probably could have made that look cooler than writing it in English, but whatever. Then all entries, elements of A inverse must also be integers. Okay, whoa, hold on. First off, in the book, they had this guy for me. I don't know if this was on the digital copy or just my physical copy. That does not make sense. It does not make sense to have entries in a determinant because the determinant is a scalar, one single number. So all numbers must be an integer. I don't know. I mean, if it were just the determinant of the inverse being an integer, they wouldn't have used the word entries. So I don't really know why they would have said that. So anyways, I'm saying that it's without that. It's probably just a typo. I went down one road at first, and I didn't really see good in that. So I'm just going to start with a different road. So again, like I don't know what my final thoughts are on a proof ever. I just kind of I write down something. I think, did that help? No. Okay, let me try something else. And so I tried about one or two other things before I got to this path. And once I started going down the path, I was like, oh, okay, that makes sense. So if we have the determinant of A is equal to 1, and all elements, I'm going to say elements, of A are integers, comma, and, here's something else, and if A inverse is equal to 1 over the determinant of A times the adjoint of A, and you're like, wait, what? I don't know if I would have to say another if or then or whatever. Maybe I should write like then. That's probably then is better. Or also. I don't know. Anyways, it's just English. It doesn't really matter. But anyways, I wanted to make a point here. The determinant of 1 is equal to 1. This guy right here is a 1 technically. So it's 1 over 1 times this adjoint. I'll write it all out and describe it to you in a second. Is equal to the adjoint. Okay. So this is what I really wanted to get that picture right here. Okay. That's what I wanted to get. My inverse is equal to this adjoint thingy. So what is that? So let's talk about this adjoint. I think it's adjoint or adjunct, something like that. Whatever. Adjoint of A. And so what is that basically? It is a matrix of cofactors. Matrix of cofactors. Now this is kind of strange here. I don't know how to describe all this here. Because the book does a much better job of showing you pictorially of what's going on here. Is it cofactors or is it minors? See, now I'm kind of wondering because I wrote down cofactors. Pretty sure I saw cofactors. But now I'm putting in my mind, I think it was a minors thing. Just hold on one second. I got my book out here. Yeah. I think I'd rather say minors. They say cofactors, but that's not really the case. So let me give you the formula, I guess you could say. So each element of this, let's call it B. Let's say that B equals, did I have B equals something else already? That's fine. Let's say that B equals this adjoint of A, okay? This is just on the side. We could talk about it for a minute here. Well, then Bij, the element Bij is equal to -1 to the power of I plus j. This is that sign of the cofactor. If you remember, plus, minus, plus, minus, plus, minus, plus, minus, plus. You remember that kind of stuff? This is a formula to make this guy work. Okay, so we got that. Times, and then it's going to be the determinant that is the minor. So I'm not going to put a little determinant. I'm going to say the minor. The minor at ij. Again, if I chose this guy, I cross through these, and I'm talking about whatever elements go right there. That's that minor, okay? So I don't know why they say cofactors, matrix of cofactors. I don't know. I like to say matrix of minors, perhaps, because there's a whole lot of minors. Let me give you a smaller example so I can show you what's going on, and then we'll jump back to this guy here in just a minute, okay? So just we're talking about this for just a moment. Let's just example. It's like I have to actually break off right here from, this is my break off from the proof. We'll get back to the proof in a minute, okay? Sometimes it takes a minute to kind of figure out what the heck's going on. Let's say I got this matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, okay? And I want to find this adjoint of the matrix. I don't know, we can call it A or whatever you want to call it, whatever. My adjoint, what would it be? Well, notice that I'm taking that 1, so that's a positive sign right there. And I'm getting rid of all these guys, and so I have this thing. So it's going to be a positive, and then I got the 5, 6, 8, 9. Notice that I'm not using the number here. That is not part of you're not using the scalar cofactor here. You're not using the scalar cofactor here. It's just the sign times the minor. That is all you're doing, okay? So forget, yeah, it's a 1, whatever, but just forget about that. When you choose a 4 here in a minute, you're not going to use 4 at all. You'll use everything else besides the 4, okay? Sorry, I want to back up so I want to keep it clean. Okay, let's just go ahead and just, no, it's okay. So I'm using that 1 right there. So here we go. Again, it would be the positive sign, like I said, 5, 6, 8, 9, which again, 5 times the 9 is 45. And then I've got 6 times the 8 is, 48, so negative 3, I believe. Let me just verify that. You know how I like to get things wrong here on the video recordings, right? Yep. Okay, cool. So we got a negative 3. So what I'm creating then is my adjoint actually looks so far like negative 3 goes right there. It's going to be a 3 by 3 with full of these numbers, okay? Well, now let's choose this guy right here, that 4. So that 4 is going to have a negative in its place, and its minor is this guy here. Again, you're not using the 4. You're not using the 4. Got to stress that. So negative 18 plus sign this time because you're going to distributing 24, 4. So I got what, a 6. So that's going to be a 6 guy, a 6 right there. And we can just keep on going. What's that guy going to be? So again, don't use the 5. That's going to be definitely a plus sign there. My minor's actually going to be, because you're doing this, you're doing this as your minor, 1, 3, 7, 9. So let me just erase. That's fine. We'll just keep it there this time because I'm done showing you my example. Again, plus sign in the front, so 9 minus 21. Again, I don't want to make a mistake here. I got a negative 12. So that goes right here. Very slow process to kind of make this thing. But that's not the point. We would have all these numbers here, and that's fine. What I'm trying to get at is we have this adjoint here where my inverse is equal to the adjoint, and what I'm really wanting to know is, do I have all of these new entries as integers? Remember, go back to what you're wanting. I have all these are integers in A, so then basically do I have them all in A inverse? Do I have all integers in my adjoint? Well, look at this. This is just an interesting example. These are all integers. Do I have integers so far here? Yeah. In fact, if you have integers here, you're going to 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 have integers there. You can see how I'm hop skipping all the way back. Integers, 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 integers. So I know that it might not be, I don't know if it's going to be in the book or not somewhere, but each, I'm going to have to go back to their words, cofactor of A in the adjoint of A, or I would maybe say like each element in the adjoint of A, must also be an integer given that integers are closed under addition and multiplication. Okay, let's talk about this whole closure thing here. This is kind of interesting side note, because I don't think we talked about that. This gets into a whole different side of things. This closure stuff is actually useful in like abstract algebra and other classes as well. I'm saying here that 2 plus 3 is 5, so an integer plus an integer equals an integer. I'm saying that 2 times 3 equals 6. An integer times an integer is an integer. So I'm saying that the set of integers is closed under addition and multiplication. And this is also addition with negative numbers, and integers include negative numbers, so it's all fine. You can say a negative 2 times a 3 is a negative 6. All this stuff is still fine. You're going to get an integer every time you do math with an integer. That's what I'm trying to get at here. So they're closed under addition and multiplication. Cool. Well, so I said that each element of the adjunct must be also an integer because it's closed under whatever. Well, we're done. There's nothing else to say here. We did it. That was it. We're done. So I know that was kind of like anticlimactic at the very end, but, you know, it's good enough. I hope that you're gaining from this that not just, hey, let's learn chapter 3, but also that you have to be kind of flexible with proofs. Some of my proofs were pretty strict and, you know, like straightforward. Going back to this one here, I think was probably the most straightforward, you know, formalized proof that I had done today. But compare that to this dude here, which was not formal at all. You know, I'm just kind of throwing some stuff up. Maybe I'm talking about it for a minute or so. That's okay. It kind of depends on what's going on. Give me what you can. Don't force yourself into being so formal that it's way too hard to understand even for me. Okay? So this sometimes writing it out with these dots and stuff like that, like that's okay. Like all this stuff, this is okay. That's a check mark. That's okay. I wouldn't use it on every problem, but it's certainly good enough for here. If you're wanting to use like the summation of I, j, blah, 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 and all that, I get confused. Not saying you can't do it, but I mean, that's wild. That's not normal, I would say. I mean, it's possible. Just, you know, we're still in a 200 level class. Anyways, if you have any questions, let me know. I think that this was pretty close to what you'd be doing in the quiz for this chapter, and this is a much shorter chapter than the other one. So, again, any questions, let me know. Thanks for hanging out today, guys. Have a great day.